Okay, without any delay, if I may, I would jump into the first guest speaker session, the one on renewable policies. And it's a great pleasure to see Katheline online, already ready to start. Let me just say a few words to present her. Well, Katheline is professor at the University of Sorbonne and associate chair at Paris School of Economics. She is a co-director of the Globalization Development and Environment program at the Center on Economic Research and its Applications, CEPREMAP. I think that's the right pronunciation. She's a member of the French High Council for Climate, a member of the French Economic Council for Sustainable Development. She is past president of the French Economic Association, and I think we first met in that national economic association context, and has a wide range of interest in environmental economics, well, from environmental economics to natural resources to dynamic macroeconomics and sustainable growth, lately working more specifically on climate economics and energy transition. She has a great record of publication from American Journal of Agricultural Economics to Journal of Economic Theory, Journal of Mathematical Economics, Journal of Environmental Economics and Management, Journal of Economic Dynamics and Control, and many others. Her presentation today will revolve around critical raw materials for the energy transition. And something that in a recent another online debate just last week or this week, I can't remember now, turned out to be a very important topic in the policy context. So Katheline, we are all here to hear you, and the floor is yours. You need to unmute yourself first.
Yeah, okay.
Great.
Okay, thanks a lot, Simone, for your kind words. And thanks a lot for the invitation too. Of course, as everybody else, I would have preferred to be in Florence. And I hope we can do that later on. But anyway, I'm going to present a paper that is very much work in progress. So you'll see it's not quite finished. There is no conclusion, but I think it's nice to share it with you, because I think that the problem, as you said, is an important problem from the policy point of view. So let me try to share my screen, and I will start right now. Okay, so it's a paper written with Aude Pommeret and Francesco Ricci, and it's, yeah, this is the motivation. So obviously the energy transition requires critical raw materials.
We don't see your screen, Katheline.
Yeah, excuse me?
We still do not see your screen.
Ah, you don't see the screen?
Not yet.
Okay. Why? Because on my...
Missing the last share, probably, Katheline, do you remember, after the preview?
But...
So you're previewing your window. Once you're sure, you should click on Start Sharing.
Yeah, I know, but my Zoom says that my screen is shared. So what is the problem?
Here
now
we go.
we are seeing.
Yeah, you see
yes.
you see Nice.
Fantastic. That's the best image you could send.
Okay. Okay. So yeah, as I said, critical raw materials are of economic and strategic high importance for the economy. What are these critical raw materials? They are these materials whose supply is associated with a high risk, as defined by the European Commission. And why is there a high risk? Because they are scarce, or there is no substitute with current technologies, or consumer countries are dependent on imports, or supply is dominated by one or a few producers. So there are several reasons why these materials should be critical. But in any case, they are very important for the energy transition. Here is the list of these critical raw materials as given by the European Commission for very recently, 2020. And you see that these are very various and not only rare earth elements. We think about rare earth elements when we think about critical raw materials, but they are not the only ones. There are a lot of them. These elements are also, look at this graph, they are also concentrated in some countries, like, for instance, rare earth more in China. You have the list here. You have cobalt and tantalum in Congo, in the United States, beryllium, and so on and so on. So they are concentrated very often in some countries, which increases the risk. So in the European Union, for instance, for electric vehicle batteries and for energy storage, the forecast is that up to 18 times more lithium and 5 times more cobalt is needed in 2030 compared to now, and almost 60 times more lithium and 15 times more cobalt in 2050, just for vehicle batteries and storage. So it's a huge increase. And also in the EU, the demand for rare earth used in permanent magnets, for instance, for electric vehicles, digital technologies, or wind turbines, could increase tenfold by 2050. And clearly, as the World Bank states in his very recent report, this demand for CRMs is increasing rapidly with climate ambition. For instance, for electric storage batteries, again, demand for aluminium, cobalt, iron, lead, lithium, manganese, nickel could grow at the world level by more than 100% by 2050. So it's a huge increase. Okay. Again, for the examples of minerals that are both crucial for the energy transition and also suffering from geological scarcity. Silver. Silver is very significantly mobilized in crystalline technologies. Photovoltaic is the third largest user of silver. There is a real tension on the availability of the material, and there is no possibility of substitution in the short term. Cobalt, too, is a good example. It is essential for permanent magnets in wind turbines, also in lithium-ion batteries. On the top of that, not only is it scarce, but also reserves are concentrated in Congo, posing geopolitical risk. Okay. So clearly there is a need to mobilize more mineral resources to build the energy infrastructure essential for the transition. And the point we want to make here is that this is generally not taken into account by public policy up to now, or not really. We wonder too whether, because of this new scarcity, let's say, we wonder whether the energy transition simply pushes the boundaries of scarcity. We have been in the past much concerned with the fossil fuel scarcity. Now we have understood that fossil fuel scarcity is not actually a problem. The real problem is the scarcity of the carbon budget. But are we just pushing this into a new scarcity, the mineral scarcity? This is also a point we are interested in. Okay, so the solution, of course, should be to reduce the dependence of energy transition on critical raw materials through recycling or through the discovery of technologies that do not rely on critical raw materials. And this is what we are going to study here. So what we do precisely, we build a model where the timing and other main features of the energy transition depends on the relative strength of two constraints: carbon budget first, climate constraint, and mineral scarcity, waiting on the economy. And when also there are some possibilities of recycling minerals, and there is the existence or not of a backstop technology for critical raw materials. We take into account political economy, in the sense that we are going to look at what happens if the optimal carbon tax is not feasible. And so if the planner or the regulator is going to adopt a suboptimal policy. And also we are going to look at what happens if the regulator is myopic, meaning that it takes his decision as if minerals were abundant. It doesn't see that there is this scarcity of these CRMs. And so we wonder to what extent cumulative emissions overshoot the carbon budget in this second case, and how much is the expected date of fossil phase out mistaken if the regulator is myopic. There is an abundant literature, of course, you know that, all of you know that, of microdynamic models allow tolling, where the renewable energy is modeled as an expensive backstop. Here, we do not adopt this type of modeling because we think it's not really appropriate for renewable energy. In fact, renewable energy differs from a backstop technology because production requires costly investment in capacity, and variable costs are nil, actually, or almost nil. So it's very different from the traditional way of modeling renewable energy in microdynamic models. And here we add a second point, which is that investment in renewable capacity requires these scarce minerals I'm talking about. In the literature, there is very few papers where there is minerals that are introduced and also recycling. It's recent. So there are these three papers I cite here. I don't have much time to look into the details, but let's say they do not do exactly what we do. And I think we add on this paper. Yeah. Okay. So what are our main assumptions? We design a stylized dynamic deterministic model of the optimal choice of the electricity mix between fossil on the one hand and renewables with storage on the other hand. So unlike what we do with ODE in a previous paper, here we suppose that the intermittency of renewables is solved because we have a storage device, a storage technology. So on the one hand, we have fossil, which is abundant, but dirty, it emits CO2. And on the other hand, we have renewables with storage, which is clean. Coal and solar, so the fossil and the renewable are available at zero variable costs. Coal-fired power plants already exist, so there is no problem of building a capacity. And the initial solar plus storage capacity is really small, so that investments are to be made in order to build a sizable storage capacity. It requires CRMs, which can be recycled to a certain extent or replaced by an extensive backstop. So what we do is we look at the optimal energy transition under mineral scarcity. So we solve the social planners program under the constraint of a carbon budget that cannot be exceeded. And we see that there is therefore a trade-off between using the polluting energy or a clean renewable energy requiring costly investment in green capital, relying on CRMs or a costly backstop technology. We look at the optimal trajectories, considering different potential succession of phases, depending on the strength of the two constraints. So minerals may be exhausted before or after the carbon budget is reached, depending on the relative size of the two stocks. After that, we look at public policy for the energy transition under mineral scarcity. For that, we use a decentralized version of the economy, and we compute the optimal policy, then the consequences for the energy transition of a suboptimal policy, as I said, consisting in a constant carbon tax and a feed-in premium with balanced budgets. In the case the optimal carbon tax is not feasible because of acceptability constraint. And then we look at the consequences of myopic regulation when the regulator sets a constant carbon tax in the aim of respecting the carbon budget, but does so as if minerals were abundant. So does a big mistake, actually. Okay, and also we account, as I said, for the possibility of recycling. So a look at the model. I'm not going to go too much into the details, but just to give you an idea of the social planners program. Here it is without recycling. We start by looking at what happens without recycling, and we will introduce recycling later on. So it's simple, very simple model. You have electricity, small e, which may be produced by fossil, X, or renewables, phi y. So y is the capacity, and phi is measures how electricity you get from this capacity. And the two, fossil and renewables, they are perfect substitutes in electricity generation. Okay, and the consumers derive utility from electricity consumption. You have an investment cost to build the renewable capacity, I. So this is the cost, C of I. And this cost is a cost in terms of minerals, M, or the backstop that we are going to suppose is very expensive. Again, the backstop and the minerals in investing for renewable capacity are substitutes. And also you have to pay here the cost of the backstop if you use it. And this the unit cost of the backstop is very, very high, so that it is not going to be used in the first place. Capital X is the carbon budget. No, it's emission accumulated into the atmosphere. So it changes, it increases with emission that depends on fossil use. And then Y dots is the accumulation of renewable capacity. So it increases with investments, but also it depreciates at a rate delta. And M is the stock of minerals that decreases with the use of minerals. We have positivity constraint. We have a carbon budget, X bar that cannot be, we cannot emit more than that. Cumulated emission cannot be more than that. And that's it. We have an initial stock of minerals. So we solve this model, and what we show is that, of course, you have different solutions depending on which scarcity binds first. Here I show you the solution for the case where the carbon budget is more constraining than mineral scarcity. We suppose that climate policy is tough. Okay. In this case, we have a first phase where we use fossil, X is positive. We use the minerals to build up the capacity, and we don't use the backstop to minerals. In this phase, carbon ceiling and mineral scarcity is not binding. What we see is that fossil fuel is used such that the marginal utility of electricity consumption is equal to the carbon value, lambda. Also, we see that the total marginal cost of using minerals to invest in green capital is equal to the shadow value of green capital, mu. The total marginal cost of using mineral being C prime of M, the investment cost, plus the scarcity rent on minerals. This is relevant if the shadow value of green capital is higher than the scarcity rent of mineral in the ground, of course. And then this phase takes place as the scarcity rent on minerals is smaller than the unit cost of the backstop, which explains why the backstop is not used. Then we have the Autoling rule on the carbon value and the scarcity rent of minerals. And then we obtain a dynamic system in Y, solar capacity, and mu, its shadow price, for this phase. And finally, this phase ends at a date Tx, such that for the first time, fossil use becomes equal to 0, and the carbon budget is exhausted. Okay. Then we have a second phase where you have no fossil fuels anymore. It is a clean phase, and to build up renewable capacity, only minerals are used, no backstop. Again, we get a dynamic system in Y and mu. This phase ends when the cost of minerals and backstop become equal, and it is precisely the date at which the mineral stock is exhausted and minerals are replaced by the backstop. Okay. And then in the third phase, you have no fossil anymore, no minerals anymore. We use the backstop. Green investment consists exclusively of the backstop technology, and the dynamic system in Y and mu converge to the steady state, Y star and mu star, defined by these equations. I'm not going to go into the details. This steady state is a saddle path, and having this steady state, we are able to go back to the first phase and to compute everything analytically. Again, this sequence is optimal only for a relatively stringent climate policy, large mineral stocks, and a small initial green capacity, and for specific configurations of costs, in particular, an expensive backstop to the minerals. Okay, I'm not going to go into the details, of course, of the other cases, but it is just to show you what we can obtain in this particular case of a relatively stringent climate policy and large mineral stock. So then I switch to the decentralized economy to look at policy. We have a representative electricity consumer. We have utilities producing electricity from either fossil resources or green capital that they own. We have the owners of mineral resources, the owner of fossil resources, and the regulator. The investment in green capital by utility mobilizes either mineral resources or the backstop. Again, markets are competitive, and there are three potential policy tools: a tax on carbon emission, a feed-in premium for electricity produced from green capital, and lump sum transfers to the household so that the public budget is in equilibrium. Electricity consumers, they face a purchaser price of electricity, PE, and they demand electricity up to the point where the marginal utility is equal to this price. Fossil producers there are no extraction cost and no scarcity. They do not take into account, of course, the climate constraints. So they supply their the fossil to no price. The price is equal to zero. Critical raw materials producers, there is no extraction cost as well, but there is scarcity, so the price is not zero, it is equal to the scarcity rent. And power producers, so this is a bit more complex, they solve an intertemporal program based on the expected evolution of the electricity price, the prices of inputs, and policy tools. So this is what the program looks like. They maximize intertemporal profits, basically. And they take into account the fact that there will be eventually a carbon tax sigma, a feed-in premium sigma on the renewables, and a carbon tax tau on the fossil inputs. They are going to pay the carbon tax, and they are going to receive possibly the feed-in premium. So again, we are able to solve this problem. In the equilibrium, there are again three phases. First, the electricity is produced with fossil complemented with renewables, and investment in renewable capacity using minerals takes place. Then fossil is abandoned, electricity is only clean, and investment in capacity takes place using minerals, and then investment in capacity uses only the backstop because minerals are exhausted. The optimal policy, of course, is straightforward. The government maximizes social welfare under the climate constraints. The optimal policy is to put in place a carbon tax equal to the optimal value of carbon in the centralized solution. And there is no feed-in premium, and tax revenues are transferred lump sum to the consumers. This is as usual. More interesting the case where there are political economic consideration, acceptability issues, which prevent the planner, the regulator, from making the carbon tax increasing in time. Is constraints on the regulator, on the choice of the policy instruments. And so we studied a suboptimal policy where the carbon tax is constant. It reminds us of the Gilets jaunes case in France, protest in France 2 years ago, where the carbon tax increase was stopped. And now the carbon tax is constant, and we wonder really in France if it will be ever possible one day to make it increase again. So we are in this case, carbon tax is constant, and the proceeds are used to subsidize investment in renewable, which is acceptable, of course. The only choice left, excuse me, there is a mistake, left to the regulator is the one of the carbon tax, because we make the assumption that all the proceeds of the carbon tax are used for the feed-in premium. So the feed-in premium is determined by the balanced budget condition. Of course, this implies that when fossil is phased out, there is no receipts, no proceeds from the carbon tax. So feed-in premium is nil as well. And the carbon tax is set at the level ensuring the respect of the carbon budget. So we do simulations because we are not able to compute everything analytically. We do simulation using this specification, log utility and quadratic investment cost. The parameters take values that do not mean anything really. It is just illustrative simulations. And maybe this graph, the carbon tax and feed-in premium. In black, you have the optimal carbon tax increasing in time, no feed-in premium. In blue, you have the case where you have the suboptimal case. So the flat line is the carbon tax, and the decreasing curve is the feed-in premium. Okay, we see that to respect the carbon budget, with the initial small renewable capacity, there needs to be a high feed-in premium initially. And so a high carbon tax is required initially as well. And so in this case, in the case we have studied, the initial carbon tax is higher initially than at the optimum. So we may wonder whether we really solve with this suboptimal policy the acceptability issue. Because, okay, the carbon tax is not going to increase in time, but we have to set it. The regulator has to set it as a high level to respect the carbon budget. Then what we can say is that fossil is exhausted very much later. Phasing out of fossil is very much delayed in this case, because of course, as the initial carbon tax is higher, fossil is going to be used, lower quantity of fossil is to be used at the beginning of the planning horizon. And as the total quantity of fossil emitted is the same in the two cases, fossil is going to last longer, of course. So the phasing out of fossil is delayed. Also, we can see that the stock of green capital is going to increase faster in the suboptimal case because of the feed-in premium, but the steady state in the end is the same. You see here investments in green capital, so it's going to be much more faster at the beginning and lower later on. Then I switch to the case, I'm going to accelerate a bit maybe. I switch to the case of myopic regulation. In this case, the regulator, and only her, is not aware that minerals used for investment in green capital are scarce. He plans energy transition as if minerals were abundant. So what he does, more precisely, is that he observes the initial price of minerals, and he thinks the price is going to remain this one forever. Okay, and on the top of that, he does not imagine that the electricity producer will ever want to use the backstop, because he thinks that minerals are completely abundant, totally abundant. So in the first step, what we do is that we model the economy as the regulator does in the decentralized equilibrium case, which allows us to determine the constant carbon tax to which the regulator commits from the start as a function of the initial observed price of mineral. And then in the second step, we let the agents act according to the policy instruments the regulator has put in place. And of course, the economy is not going to behave as the regulator has planned, because there is an actual scarcity of mineral resources. And so we look at what happens to the real economy when the regulator has made this mistake. So the main mechanism is that ignoring minerals exhaustibility boils down to underestimating their real costs, hence the real cost of the energy transition. So underestimating that, the regulator undersizes environmental policy, the carbon tax it sets is too small, fossil use is higher, and as a result, cumulative carbon emissions overshoot the targets. Okay, there is a mistake that makes emissions overshoot the carbon budget. So here I compare the different scenarios, the optimal policy, the suboptimal policy I've talked about before, the myopic forecast, meaning the situation the planner thinks the economy is going to be in. And then the last column is what is actually going to happen. Okay. And maybe what is interesting is that in the case of the myopic regulation, let's say what is the most interesting result. The steady state, no, this is, the fossil phase out date in the optimal policy, it's 17. In the suboptimal policy, it's much more later, as I said, but in the myopic regulation, it's much more later again. So energy transition is completely, it doesn't occur as it should, clearly. What can I tell you too? Yeah, the initial carbon tax in the case of the myopic forecast is smaller than in the case of the suboptimal policy. And this explains why the cumulative carbon emission overshoot the carbon budget. Okay, so just a word.
Katheline?
Yeah?
Just 1 minute, I would say.
Okay, but I am finished.
Okay, great.
Just a word about recycling minerals. So we redo the model, introducing the possibility of recycling. But there is a rate of recycling, the depreciated green capital, delta Y. So what is depreciated may be recycled at a rate, alpha, and this has a cost that we model very simply like that. And to focus on plausible cases where recycling is limited, we suppose that the cost of perfect recycling, alpha is equal to 1, is larger than the cost of using the backstop. And so what we obtain is that the transition is achieved in 4 phases, which are a bit different in the case where the recycling cost is high or in the case where the recycling cost is low. Because of course, clearly it's quite intuitive. If the recycling cost is low, recycling is going to take place before the exhaustion of fossil, while when it is high, recycling is going to start after the exhaustion of fossil. And in any case, what happens when there are recycling possibilities is that there is a smaller initial carbon value, hence more fossil fuel used in the short run. Fossil is phased out sooner because of that, as a consequence of that. Mineral stock is exhausted later, and there is a higher steady state renewable capacity, allowing higher electricity consumption in the long run. And all these effects are on the larger since the cost of recycling is lower. So of course, as intuition tells us, recycling is beneficial, all the more since its cost is low. And also we can observe something like a green paradox, which is that when there are recycling possibilities, economy is going to consume more fossil now. Because there are less, because of course the climate constraint is going to be less tough because there is this new possibility of recycling, so that we are going to consume more carbon now. I think that's about all I wanted to tell you. And thank you for listening.
Thank you, Katheline. It's a very rich and interesting model. We have a few questions, 3 questions to be honest, for 3 minutes for questions. Let me see if there are questions, or otherwise I would like to pose one, and then I see Karsten. Very briefly, you show us that a myopic regulator would increase the phase-out time consistently. Could you tell us something on the last scenario when you have recycling? How much this would constrain the or reduce the phase-out time, accelerate the phase-out, so to speak?
Yeah, we have not redone the simulations in the myopic regulator case with recycling. I must say, as I said at the beginning, it's a work in progress, so we are still doing simulations. What we would like to do, of course, is to put real data on that, because here we have just illustrative simulations where the result don't mean anything actually, just this the way variables move is really sure. So I'm not sure I can answer to that. Yeah.
Karsten?
I think you show how important this recycling is going to be for our developments. So where do you see the main policy obstacles? Is it product design? Is it technology innovation? Is it the infrastructure for the recycling that need to be tackled, and perhaps early on?
I'm not sure, but I think that maybe policymakers didn't really take the extent to which recycling is going to be important. They are not really aware now, I think, of that. So I think the obstacle, maybe one of the obstacles, maybe this one, that they have to become conscious of the importance of recycling. Then there are probably technological obstacles. In the European publication and the World Bank publication, very recent this year, they say something about that, about to which extent the different critical raw materials are recyclable, to which extent it is possible technically. And for some of them, it's very small actually. So you may recycle maybe 5 or 10% of the total source. For some of them, it's very small. So I think probably we need a lot more technological innovation to improve that.
There is one question from Luca Mazzotti, who was asking if you know whether the French government is taking into account the mineral scarcity in its programmation pluriannuelle de l'énergie.
Programmation pluriannuelle de l'énergie. No. Actually, they are not taking into account it. No. I know positively they don't.
Yeah, that's for sure. And I think Paul wanted to pose a question as well, and probably a last question, then we have to close.
Yeah, thank you very much, Kathleen. Really interesting stuff, and so important to be bringing in the critical raw materials. I'm thinking back to an International Resource Panel report on the recycling of these critical materials. And the current recycling rates are really, really, really low. I mean, like 2-3%, if that. And as you said, the abilities to recycle with current technologies, some of these materials are quite limited because they're available in very small quantities in particular devices. And I just wonder whether how you're modeling the cost of the recycling processes. I mean, assuming that there is innovation, and obviously was the theme of my talk, assuming there is innovation to make it more possible, how are you thinking about what the cost of these recycling processes are going to be, and how are they factored into your model?
At the moment, the cost of recycling is just increasing and convex. So it's an increasing and convex function of the rate, the recycling rate. So we do not introduce the fact that there could be learning also in recycling, or that could be better technologies. It is just increasing and convex function of the rate. Yeah. So it's yeah. I think that when we are going to go to the empirical application, of course, we will have to look that in much more details. What are the real costs? What do the real costs look like, and so on? Yeah.